The hum is always there, not audible, not exactly, but present in the way gravity is present, in the way time moves forward without asking permission. Earth's magnetic field wraps around the planet like an exhale that never ends, stretching tens of thousands of kilometers into space, bending under the pressure of the solar wind, flexing with the rotation of molten iron 3,900 kilometers below the surface. It is invisible to human eyes, undetectable to human skin, but instruments feel it, they measure it, they record its trembling, scattered across continents. Magnetometers stand in quiet stations, some on university campuses, some in remote observatories where the nearest road is an hour away and the sky at night is properly dark. Each instrument consists of sensors that detect the strength and direction of the magnetic field at that precise location, sampling the field every second or every few seconds, translating invisible force into voltage, voltage into numbers, numbers into long data sets that accumulate year after year. The readings are measured in nanoteslas, a unit so small that Earth's entire field at the surface registers between 25,000 and 65,000 nanoteslas depending on latitude. A refrigerator magnet, held close, would drown the signal entirely, but the instruments are placed carefully, away from power lines, away from metal infrastructure, away from the electrical hum of human civilization as much as possible, though true isolation is rare now, even in Antarctica, where some magnetometers sit on ice older than most mountain ranges. There is interference from the station itself, from equipment, from the occasional plane passing overhead. The art of magnetometry is not just in measuring the field, but in filtering the noise, in separating the planetary signal from the static. What they measure is ancient. The field itself is generated by the geodynamo, a process that has been running for at least 3.5 billion years, possibly longer. Deep in the outer core, liquid iron moves in vast convective currents, driven by heat escaping from the even deeper inner core, by the cooling of the planet as a whole, by forces that operate on timescales humans will never directly witness. As this molten metal flows, it carries electric charge with it, and moving electric charge generates magnetic fields. The fields, in turn, influence the flow of the metal, creating feedback loops of staggering complexity. No one has ever seen the outer core. No instrument will ever be placed there. The pressures are too great, the temperatures too extreme. What we know about it comes from seismic waves, from magnetic observations at the surface, from models run on supercomputers that try to replicate the swirling chaos of iron in the dark. The field is not stable. It wanders. The North Magnetic Pole drifts across the Arctic at tens of kilometers per year, pulled by changes in the flow patterns below. Every few 100,000 years, on average, the field reverses entirely. North becomes south, south becomes north, though the process is neither quick nor clean. During reversals, the field weakens, fragments into multiple poles, flickers like a failing bulb, and then eventually settles into a new configuration. The last reversal happened 780,000 years ago, which means the current field is overdue by some measures, though overdue is a human word, and the geodynamo does not keep appointments. On shorter time scales, the field pulses and shivers. Solar storms send waves of charged particles toward Earth, compressing the dayside magnetosphere and stretching the night side into a long tail that streams away from the sun. These interactions generate magnetic substorms, sudden releases of energy that cause the field at the surface to spike or drop by tens or even hundreds of nanoteslas over the course of minutes. Auroras accompany these events, visible reminders of invisible processes. The magnetometers record it all, every fluctuation, every tremor. And sometimes they record things that are harder to explain. In late 2024, several magnetometer stations registered small, synchronized variations in the field, tiny changes, less than 1 nanotesla in amplitude, lasting only a few minutes. The variations appeared first at high-latitude stations in northern Canada and Scandinavia, then propagated equatorward over the following hours. There was no corresponding solar storm. No coronal mass ejection had been detected. The sun was quiet. The interplanetary magnetic field measured by satellites upstream of Earth showed no unusual structure. What had happened in the days leading up to the anomaly was the passage of 3I/Atlas, Comet 3I/Atlas, the third confirmed interstellar object to pass through the solar system, after 1I/Oumuamua in 2017 and 2I/Borisov in 2019, entered the inner solar system on a hyperbolic trajectory, meaning it was not bound by the sun's gravity. It had come from somewhere else, from another star system, perhaps one of the young clusters in the direction of Cygnus. Though tracing its origin precisely is difficult, interstellar space is vast and mostly empty, and objects drift for millions of years between ejection and arrival. By the time 3I/Atlas crossed the orbit of Mars, it had been traveling for longer than human civilization has existed. It was not large. Estimates based on brightness and albedo suggested a nucleus perhaps 2 to 3 kilometers across, smaller than many comets native to our solar system, but large enough to carry volatiles, water ice, carbon dioxide ice, methane, ammonia, that began to sublimate as it approached the sun. A faint coma formed, and then a tail. Though neither was spectacular by cometry standards, amateur astronomers tracked it. Professional telescopes imaged it in multiple wavelengths. Spectrographs analyzed the light reflected and emitted by the gases in the coma, searching for chemical signatures that might hint at the conditions around the comet's parent star. No one expected it to interact with Earth's magnetic field. The comet never came particularly close to Earth. Its closest approach was roughly 40 million kilometers, about a quarter of the distance to the Sun, well beyond the orbit of the Moon. But space is not empty, and magnetic fields extend far beyond the objects that generate them. The Sun's magnetic field, embedded in the solar wind, fills the entire heliosphere. Earth's magnetosphere carves out a cavity in that wind, and comets, when active, are surrounded by clouds of ionized gas, plasma, that can carry their own magnetic disturbances. The flicker in the magnetometer data lasted 4 to 11 minutes, depending on the station. The amplitude was small enough that it might have been missed entirely if not for the global networks that pool data and apply statistical filters to identify coherent signals. Intermagnet. The global network of magnetic observatories archives data from more than 100 stations. Supermag combines data from even more, applying corrections for baseline drift and local effects. When researchers later examined the records from the period of 3Y/Atlas's approach, the pattern emerged, subtle, synchronized, unexplained. It could have been coincidence. The field fluctuates constantly. Micropulsations occur all the time, generated by interactions between the solar wind and the magnetosphere, by atmospheric dynamics, by crustal magnetic anomalies. Finding a pattern in noise is easy if you look hard enough. The human brain is wired to see structure, to connect dots, to invent causality where there may be none, but the timing was curious, and the propagation pattern, high latitude first, then equatorward, matched what one might expect from a disturbance entering through the polar cusps, the regions where the magnetosphere is thinnest and solar wind particles can penetrate more easily. So the question remains, suspended in the data like sediment in water, did an interstellar comet, passing 40 million kilometers from Earth, leave a trace in the planet's magnetic field? Or is this simply the story humans tell when they find a coincidence and cannot resist giving it meaning? The magnetometers do not answer. They only record. Second by second, nanotesla by nanotesla, the hum beneath everything continuing. The iron moves in the dark. It has been moving for billions of years, longer than there have been eyes to see daylight, longer than there have been continents shaped the way they are now, longer than oxygen has dominated the atmosphere. The outer core is a shell of liquid metal approximately 2,200 kilometers thick, wrapped around the solid inner core, itself a sphere of crystallized iron-nickel alloy about 1,200 kilometers in radius. The temperature at the boundary between them exceeds 5,000 degrees Celsius, hotter than the surface of the Sun, yet the inner core remains solid because the pressure is so immense that atoms cannot escape into liquid motion. 330 gigapascals, 33 million times the pressure at Earth's surface. The outer core, slightly cooler, remains liquid, and within that liquid, vast currents flow. They are not rivers in any familiar sense. There are no banks, no channels, no surfaces. The flow is three-dimensional, chaotic, turbulent on scales ranging from centimeters to thousands of kilometers. Convection drives the motion, heat from the inner core rising, cooler material sinking, but the picture is complicated by the rotation of the Earth, which deflects the flow into spiraling columns aligned roughly with the rotation axis. These columns are called Taylor columns, named after the physicist who first described their dynamics. They twist and merge, split and reform, in patterns that shift over years, decades, centuries. The iron in the outer core is not pure. It contains lighter elements, sulfur, oxygen, silicon, whose presence lowers the melting point and affects the density. As the inner core slowly grows, crystallizing from the surrounding liquid at a rate of about 1 millimeter per year, it preferentially incorporates iron and nickel, leaving the lighter elements behind. This creates compositional buoyancy in addition to thermal buoyancy, adding another layer of complexity to the convective flow. And all of this motion, thermal, compositional, rotational, generates magnetic fields. The process is called the geodynamo, and despite decades of study, despite sophisticated numerical simulations that require some of the world's most powerful supercomputers, it is not fully understood. The basic mechanism is known. Moving conductive fluid in the presence of a magnetic field induces electric currents, and those currents generate new magnetic fields, which can reinforce the original field in a self-sustaining feedback loop. But the details are ferociously complicated. The equations governing magnetohydrodynamics, the physics of electrically conducting fluids in magnetic fields, are non-linear, coupled, and difficult to solve even in simplified geometries. Simulations help. Modern geodynamo models can reproduce many features of Earth's magnetic field, the dipole structure, the westward drift of field features, the occasional reversals, but they require approximations. The viscosity of liquid iron at core conditions is uncertain. The thermal conductivity is debated. The exact composition of the outer core is inferred but not known. And even the best simulations cannot resolve the full range of scales involved, from the thickness of the outer core down to the smallest eddies where turbulence dissipates into heat. What emerges from the dark iron, what reaches the surface and extends into space, is a field that is mostly dipolar, like a giant bar magnet tilted about 11 degrees from the rotation axis, but with significant non-dipolar components, quadrupole terms, octupole terms, higher-order multipoles, all present in varying strengths. At the surface, these components create regional variations in field intensity. Over the South Atlantic, there is a region where the field is notably weaker, a feature called the South Atlantic Anomaly, where charged particles from space penetrate more easily and can damage satellites passing through. The field is not symmetric. The northern and southern hemispheres have different field strengths. The magnetic poles do not sit at the geographic poles, nor are they opposite each other through the center of the Earth. The North Magnetic Pole currently wanders across the Canadian Arctic towards Siberia, accelerating in recent decades for reasons that are still being investigated. The South Magnetic Pole drifts more slowly across Antarctica. These asymmetries reflect asymmetries in the core flow. The geodynamo is not a simple, uniform process. Different regions of the outer core contribute differently to the surface field. There are regions of strong radial flow and regions where the flow is mostly horizontal. There are jets, narrow currents of faster-moving iron, that appear in simulations and are inferred from observations of rapid field changes called geomagnetic jerks. These jerks are sudden accelerations in the rate at which the field is changing, lasting a year or two. And they suggest that something in the core flow shifted abruptly. Though what exactly remains unclear, paleomagnetic studies, analyses of magnetic minerals in rocks, revealed that the field has existed for at least 3.5 billion years. Tiny crystals of magnetite in ancient rocks from South Africa and Western Australia preserved the direction and intensity of the field at the time the rocks formed. The field was weaker then, perhaps half its current strength, but it was present. This is important. Without a magnetic field, Earth's atmosphere would be more vulnerable to erosion by the solar wind. Charged particles from the Sun would strip away lighter atmospheric gases over geologic time. Mars, which lost its global magnetic field early in its history, lost most of its atmosphere. Venus, which never had a strong dynamo or lost it long ago, has an atmosphere but no magnetosphere. Earth kept its field, and the field kept the atmosphere, and the atmosphere allowed liquid water, and liquid water allowed life. Though the chain of causality is not quite that simple, life is resilient. Life adapts. But certain kinds of complexity may require certain kinds of protection, and the magnetosphere provides that protection in a way that is easy to overlook because it is invisible. The field reverses irregularly. The intervals between reversals range from tens of thousands to tens of millions of years. The current interval, the Brunhes chron, named after the geophysicist Bernard Brunhes, who first identified reversed magnetizations in volcanic rocks, has lasted 780,000 years. Before that, the Matuyama chron, reversed relative to today's field, lasted nearly 2 million years. The pattern extends back hundreds of millions of years, recorded in the seafloor where new crust forms at mid-ocean ridges and preserves the field direction as it cools. During a reversal, the dipole field weakens, sometimes to a small fraction of its normal strength. The non-dipolar components become more prominent. Multiple magnetic poles appear at the surface. The field geometry becomes chaotic. Simulations suggest that reversals are triggered by instabilities in the core flow, but predicting when the next reversal will occur is impossible with current understanding. The field is weakening at present. It has lost about 9% of its strength over the past 2 centuries, but this does not necessarily mean a reversal is imminent. The field has weakened and recovered before. The iron moves, indifferent to the surface, indifferent to the life clinging to the crust, indifferent to the instruments measuring the field. It flows according to the laws of thermodynamics and electromagnetism, and those laws do not care about human timescales or human concerns. The outer core has been convecting for eons and will continue convecting for eons more, until the planet cools enough that the geodynamo shuts down. That will not happen for billions of years. The Sun will become a red giant first, expanding to engulf the inner planets, rendering all questions about Earth's magnetic field moot. But for now, the field persists. It surrounds the planet. It channels charged particles toward the poles, where they collide with atmospheric gases and create auroras. It shields satellites and astronauts from some of the radiation in near-Earth space. It allows migratory birds and sea turtles to navigate across thousands of kilometers, sensing field direction with biological magnetoreceptors whose precise mechanisms are still being studied. and it creates a background against which disturbances can be measured. When the solar wind gusts, the magnetosphere compresses. When coronal mass ejections arrive, geomagnetic storms erupt. When the interplanetary magnetic field turns southward, magnetic reconnection occurs at the dayside magnetopause, injecting energy into the system. All of these events leave signatures in magnetometer data, signatures that can be studied, modeled, predicted to some degree. But a passing interstellar comet, that was not in the models. That was not something anyone had thought to look for. Until, perhaps, the data suggested otherwise. The iron continues its dark convection. The field continues its invisible breathing. And somewhere, archived on servers in multiple countries, a few minutes of magnetometer data from late 2024 wait for someone to decide whether they mean something or nothing at all. Space is not empty, though it looks that way. Between the stars, between the planets, in the vast reaches where light takes years to cross from one side to the other, there is matter, hydrogen, mostly, 1 atom per cubic centimeter in the interstellar medium near the Sun, fewer in the voids between spiral arms, more in the dense molecular clouds where stars are born. There is dust, grains of silicate and carbon, coated with ice, smaller than the width of a human hair. There are magnetic fields, weak but pervasive, threading through the galaxy. There is radiation, cosmic rays, photons across the spectrum, neutrinos passing through everything without interaction. And occasionally, there are objects, solid bodies, comets, asteroids, rogue planets ejected from their birth systems. They drift in the cold, moving at tens of kilometers per second relative to nearby stars, their surfaces sculpted by micrometeorite impacts and radiation weathering over timescales that make Earth's geologic history seem brief. Most of these objects will never encounter another star system. Space is too large, stars too far apart. The average distance between stars in the solar neighborhood is about 4 light-years, roughly 40 trillion kilometers. An object moving at 30 kilometers per second would take 40,000 years to cross that distance. Most interstellar objects will wander the galaxy for billions of years without ever coming close to another sun. But some do. Statistically, a few interstellar objects must pass through the inner solar system every year, though most are too small or too dark to detect. Until recently, none had been confirmed. Astronomers had hypothesized their existence, ejection mechanisms were well understood, and every planetary system likely produces a population of wanderers. But observation is harder than theory. Oumuamua changed that. Discovered in October 2017 by the Pan-STARRS telescope in Hawaii. Oumuamua was unlike any comet or asteroid previously observed. Its trajectory was hyperbolic, meaning it was moving too fast to be bound by the sun's gravity. It had come from interstellar space and would return to interstellar space. Its shape was inferred to be highly elongated, possibly 10 times longer than it was wide. Though this remains debated, it showed no visible coma or tail, despite passing close enough to the sun that ices should have sublimated. And it exhibited a small, non-gravitational acceleration as it left the inner solar system, a push that could not be explained by gravity alone. The acceleration sparked speculation. Some proposed outgassing from ices hidden beneath a radiation-darkened crust. Others suggested radiation pressure acting on a thin, light sail-like shape. A few ventured further into hypothesis space, suggesting artificial origins, though no evidence supported this, and most scientists regarded it as implausible. The data were ambiguous. Oumuamua was observed for only a few weeks before it became too faint to track, and many questions remain unanswered. 2 years later, 2I/Borisov arrived. Discovered in August 2019 by amateur astronomer Gennady Borisov using a telescope he built himself. This second interstellar visitor was more clearly a comet. It had a visible coma and tail. Spectroscopic observations detected water vapor, carbon monoxide, and other volatiles outgassing from the nucleus. Its composition appeared similar to comets formed in the solar system, though with a higher carbon monoxide abundance, suggesting formation in a colder environment. It passed through the inner solar system, rounded the Sun, and departed, observed by telescopes around the world until it faded beyond detection limits in mid-2020. 2 confirmed interstellar objects in 3 years suggested that such visitors might be more common than previously thought. Estimates were revised upward. Perhaps several pass through the inner solar system every year. Perhaps hundreds pass through the outer solar system, undetected because they are faint and distant and we are not looking in the right places at the right times. And then 3I/Atlas appeared. It was detected in June 2024 by the Atlas Survey, the Asteroid Terrestrial Impact Last Alert System, a network of telescopes designed to identify near-Earth asteroids and comets. The object was faint, moving rapidly against the background stars, and its orbit, when calculated, was clearly hyperbolic, eccentricity greater than 1, orbital energy positive. Another visitor from the dark between stars. Initial observations suggested a small nucleus, perhaps 2 to 3 kilometers across. Though cometary sizes are difficult to estimate because what we see is mostly the coma, the cloud of gas and dust surrounding the nucleus, and the nucleus itself is often hidden. As 3I/Atlas approached the Sun, warming from the feeble heat of distant starlight to the stronger radiation closer in, ices began to sublimate. Water ice first, at temperatures above about 150 Kelvin, then carbon dioxide, carbon monoxide, methane. The volatiles escaped the weak gravity of the nucleus and expanded into space, forming a coma that grew to hundreds of thousands of kilometers across, large enough to swallow several Earths. Spectroscopy revealed familiar molecules, water, hydroxyl radicals, cyanogen, diatomic carbon. The abundances were within the range observed for solar system comets, though subtle differences hinted at formation conditions that might have been slightly colder, slightly richer in volatile ices. The DH ratio, the abundance of deuterium relative to hydrogen in water molecules, was measured by several observatories. It was higher than Earth's ocean water, lower than some other comets, consistent with formation in the outer regions of a protoplanetary disk where temperatures were low enough for ices to condense, but not so low that deuterium enrichment became extreme. The tail formed as solar radiation, and the solar wind pushed the coma material away from the Sun. Cometary tails are not single structures, but typically 2. A dust tail, broad and curved, composed of small solid particles that follow Keplerian orbits and lag behind the comet, and an ion tail, narrow and straight, composed of ionized gas pushed directly away from the Sun by the solar wind's magnetic field. The ion tail can stretch for millions of kilometers, sometimes tens of millions. A glowing filament visible only because the ions fluoresce under solar ultraviolet radiation. It is the ion tail that matters for magnetism. When volatiles sublimate from a comet's nucleus, some fraction of the molecules are ionized by solar ultraviolet light and by the solar wind itself. These ions are charged particles, and charged particles interact with magnetic fields. The solar wind carries the Sun's magnetic field with it as it streams outward, the interplanetary magnetic field, or IMF, a structure shaped by the Sun's rotation into a spiral pattern called the Parker spiral. When cometary ions enter this field, they are picked up by the flow, accelerated to solar wind speeds, and carried away from the comet. This interaction creates disturbances, the solar wind, moving at 300 to 800 kilometers per second, encounters a cloud of relatively slow-moving ions around the comet. Momentum is exchanged, magnetic field lines are draped around the obstacle, waves propagate through the plasma, alpha waves, magnetosonic waves, carrying energy and information about the interaction downstream and upstream for a large, active comet close to the Sun. This interaction can be substantial. The Coma produces so much gas that the solar wind cannot penetrate directly to the nucleus. Instead, a bow shock forms upstream, a boundary where the supersonic solar wind abruptly slows and heats. Between the bow shock and the nucleus, a region called the Coma envelope is relatively shielded from the solar wind, though the magnetic field still penetrates and shapes the ion tail. 3I/Atlas was not large. Its gas production rate, estimated from brightness and spectroscopic measurements, was modest compared to famous comets like Hale-Bopp or Halley, but it was producing ions, and those ions were being swept into the solar wind, and the solar wind was carrying them outward into the heliosphere. At its closest approach to the Sun, perihelion, reached in late October 2024, 3I/Atlas was approximately 1 astronomical unit from the Sun, roughly the same distance as Earth, but its trajectory was inclined to the ecliptic plane, and it did not pass particularly close to any planet. Closest approach to Earth occurred in mid-November, at a distance of about 40 million kilometers, roughly a quarter of the distance to the Sun, well beyond the Moon's orbit, well outside the magnetosphere. No direct interaction was expected. 40 million kilometers is far. The magnetosphere, compressed on the day side by the solar wind, extends only about 10 Earth radii in that direction, roughly 64,000 kilometers. On the night side, the magnetotail stretches much farther, millions of kilometers. But 3I/Atlas did not pass through the tail, and yet the flicker appeared in the data. The flicker was small. In the context of geomagnetic activity, it barely registered. The disturbance amplitude measured between 0.3 and 0.7 nanoteslas, depending on the station, less than 1 part in 50,000 of Earth's total field strength at the surface. Solar storms can produce variations of hundreds or even thousands of nanoteslas. Magnetic substorms routinely create swings of tens of nanoteslas over minutes to hours. The day-to-day variation in the field due to solar quiet currents, regular ionospheric current systems driven by solar heating, can be tens of nanoteslas. Against this background, 0.5 nanoteslas is nearly nothing. But it was there. And more importantly, it was coherent. Coherence is what separates signal from noise. Random fluctuations occur constantly. Instrumental drift, temperature variations in the sensors, electromagnetic interference from distant thunderstorms, perturbations from local crustal magnetic anomalies as the observation site moves through Earth's rotation, all of these contribute to variations in magnetometer readings. At any single station, a brief 0.5 nanotesla fluctuation might be dismissed as noise. Unremarkable, not worth investigating. But when the same fluctuation appears at multiple stations, separated by thousands of kilometers, occurring within minutes of each other and propagating in a consistent spatial pattern, that suggests something real happened. Something that affected the magnetosphere as a whole, or at least a significant portion of it. The pattern emerged during routine data processing months after the event. Researchers analyzing magnetometer data for other purposes, studying ionospheric currents, characterizing geomagnetic jerks, investigating solar wind coupling efficiency, noticed a small, synchronized anomaly in the records from November 2024. The anomaly appeared first at high-latitude stations, Alert in northern Canada, Tromsø in Norway, Sodankila in Finland. Minutes later, it appeared at mid-latitude stations, Ottawa, Uppsala, Irkutsk. The signal weakened as it propagated equatorward, becoming barely detectable at low-latitude stations and absent at equatorial sites. The temporal structure was consistent with a disturbance entering through the polar cusps, the regions near the magnetic poles where the magnetosphere opens to the solar wind, where charged particles can penetrate more easily, where magnetic field lines connect directly to the interplanetary magnetic field rather than closing within the magnetosphere. A disturbance entering through the cusps would affect high-latitude stations first, then propagate to lower latitudes as currents and waves spread through the ionosphere and magnetosphere. But what caused the disturbance? The first check was solar activity. Geomagnetic disturbances are usually caused by the sun, coronal mass ejections, high-speed solar wind streams, solar flares. These are the primary drivers of space weather. But the solar indices for mid-November 2024 showed nothing unusual. No CMEs had been directed toward Earth in the days prior. The solar wind speed measured by satellites at the L1 Lagrange point, about 1.5 million kilometers upstream of Earth, was steady and unremarkable, around 400 kilometers per second, typical for slow solar wind. The interplanetary magnetic field strength was normal, a few nanoteslas, and its direction was not oriented favorably for strong coupling with the magnetosphere. Geomagnetic activity indices, Kp, Dist, Ae, were all low, indicating quiet conditions. If the sun had caused the fluctuation, there should have been corresponding signatures in these indices. There were none. The second check was for auroral activity. Auroras are visible manifestations of magnetospheric dynamics, occurring when charged particles precipitate into the upper atmosphere along magnetic field lines and collide with oxygen and nitrogen atoms, causing them to emit light. Strong geomagnetic disturbances almost always produce auroras, especially at high latitudes. But aurora reports from the time of the anomaly were sparse. Some observers in northern Scandinavia noted faint auroral glows, but nothing remarkable. Nothing that suggested significant particle precipitation or magnetic disturbance. The third check was for internal magnetospheric processes. The magnetosphere is not a passive structure. It has its own dynamics. Ultra-low frequency waves, ULF waves, propagate through the magnetosphere, driven by instabilities and resonances. Field line resonances occur when waves couple to the natural oscillation frequencies of magnetic field lines, creating standing wave patterns. These processes can produce localized magnetic perturbations at the surface, but they typically have characteristic frequencies and spatial patterns that did not match the observed anomaly, so the search is expanded. Someone thought to check for asteroid close approaches. None were found at the relevant time. Someone else checked for seismic activity, wondering if a large earthquake might somehow have perturbed the ionosphere. No significant earthquakes occurred in the hours before or during the anomaly. Volcanic eruptions, explosive or otherwise, were ruled out. Meteor showers. Some large meteors can create ionospheric disturbances, did not correlate. And then someone remembered the comet. 3I/Atlas had made its closest approach to Earth on November 14, 2024. The magnetometer anomaly occurred on November 15th, lasting from approximately 3:14 to 3:25 UTC at the earliest affected stations. The timing was close enough to be interesting. The comet's distance, 40 million kilometers, was far, but not infinitely far. And the comet had been active, producing ions, releasing plasma into the interplanetary medium. The hypothesis was tentative. Could cometary plasma, carried by the solar wind, somehow perturb Earth's magnetosphere from 40 million kilometers away? The physics were unclear. Cometary ions are not confined to the comet's immediate vicinity. They are picked up by the solar wind and carried outward, dispersing as they go. But 40 million kilometers is a long distance, and by the time any cometary material reached Earth's orbital region, it should have been diluted beyond detection, mixed into the vast bulk of the solar wind. unless something else was happening. Plasma disturbances propagate. They are not simply advected passively with the solar wind. They generate waves, alpha waves in particular, which are oscillations in the magnetic field and plasma velocity that travel along magnetic field lines at the alpha speed, typically a few hundred kilometers per second in the solar wind. These waves can carry information about disturbances over large distances. If 3I/Atlas's ion tail had created a significant disturbance in the interplanetary magnetic field, a kink, a density enhancement, a change in field orientation, that disturbance could have propagated as waves through the solar wind. And if those waves happened to reach Earth's magnetosphere with the right orientation and timing, they could, in principle, couple to the magnetosphere and produce observable effects. It was speculative, it was a reach, but it was testable, at least in principle. Satellite data from spacecraft monitoring the solar wind could be examined for anomalies. Models could be run. The geometry could be calculated. The work began quietly, without fanfare. A few researchers exchanged emails. Datasets were pulled from archives. Preliminary analyses were conducted. The results were ambiguous. Some satellite data showed hints of density variations in the solar wind around the relevant time, but nothing dramatic. The interplanetary magnetic field had rotated slightly, but such rotations are common. There was no smoking gun, no clear signature that screamed cometary disturbance. And yet, the magnetometer flicker remained, small, synchronized, unexplained. The question mark sat in the data, patient and unresolved. A magnetometer is, at its core, an instrument for measuring invisibility. It translates something humans cannot sense, magnetic field strength and direction, into something they can. Numbers on a screen, voltage readings, plotted graphs. The technology has existed in various forms for more than a century. Though modern instruments bear little resemblance to the early compasses and dip needles used by 19th century explorers to map Earth's field, the most common type used in geomagnetic observatories today is the fluxgate magnetometer. It consists of a core of ferromagnetic material, typically a nickel-iron alloy with high magnetic permeability, wrapped with two coils of wire. An alternating current is passed through one coil, driving the core into magnetic saturation and back, hundreds or thousands of times per second. The second coil detects the induced voltage, which depends on the external magnetic field. By comparing the induced signals, the instrument can measure the field component along the core's axis with high precision. 3 fluxgate sensors, oriented perpendicular to each other, measure the field in 3 spatial directions: north, east, and vertically downward. From these 3 components, the total field strength and direction can be calculated. The instruments are sensitive to a fraction of a nanotesla, capable of detecting changes far smaller than the background field they measure. But sensitivity brings vulnerability. Fluxgate magnetometers respond to any magnetic field, not just Earth's. A passing car with an electric motor, a power line carrying alternating current, a piece of rebar in the ground beneath the sensor, all create magnetic perturbations. Temperature changes affect the electronics. Mechanical vibrations can introduce noise. Even the diurnal heating and cooling of the sensor housing can produce slow drifts in the readings. So the instruments are isolated. Observatory sites are chosen carefully, often in remote locations far from cities and infrastructure. The sensors are placed in non-magnetic buildings, structures built without steel, using aluminum or fiberglass or wood. Temperature is controlled, or at least monitored, so corrections can be applied. The data are filtered, averaged, and compared against other stations to identify and remove local artifacts. Some observatories use additional instruments for absolute measurements. A proton precession magnetometer, for example, measures the total field strength by exploiting the magnetic properties of hydrogen nuclei when placed in a magnetic field and excited with a pulse of energy. Protons precess around the field direction at a frequency proportional to the field strength, the Larmor frequency. By measuring this frequency with high precision, the instrument determines the total field magnitude without needing calibration. These absolute measurements are used to correct drift in the fluxgate sensors. The data are sampled continuously. 1 second cadence is typical, though some stations record at higher rates. The numbers accumulate 3 field components, once per second, 86,400 seconds per day, 365 days per year, gigabytes of data per observatory. Multiply by the number of observatories in global networks, more than 100 in intermagnet, several hundred in supermag, and the total data volume becomes substantial. But large datasets enable statistical analysis. Patterns that would be invisible in a single station's records become apparent when many stations are combined. Spatial correlations can be identified. Propagation velocities can be calculated. Signals buried in noise at individual sites emerge clearly in network average data. This is how the flicker was found, not by someone staring at a single magnetogram and noticing an oddity, but by algorithms processing data from dozens of stations, looking for coherent variations, applying filters to separate global signals from local noise. The software flagged the event as a minor anomaly, not strong enough to trigger alerts, not associated with any known solar wind driver, but present nonetheless. At each affected station, the signature was slightly different. At alert, the northernmost observatory in the intermagnet network, the disturbance appeared primarily in the horizontal component, a brief increase in the northward field component, lasting about 4 minutes, with amplitude near 0.7 nanoteslas. At Tromsø, the signature was similar but weaker, about 0.5 nanoteslas. At mid-latitude stations like Ottawa, the amplitude dropped to 0.3 nanoteslas and the duration shortened to 2 or 3 minutes. The vertical component showed little change at most stations, which was consistent with the disturbance propagating horizontally through the ionosphere. The east-west component showed variations at some stations but not others, reflecting the complex current geometry. One curious feature was the timing. The disturbance did not appear simultaneously at all high-latitude stations, even those at similar magnetic latitudes. Alert recorded the onset first, at 3:14 UTC. Tromsø, roughly 90 degrees away in longitude, recorded it 3 minutes later. Sodenkila, another minute after that. This suggested the disturbance was not a simple global compression of the magnetosphere, which would affect all longitudes simultaneously, but something propagating, something with structure. The propagation velocity could be estimated from the timing delays and station separations. The result was approximately 1,500 kilometers per second, westward at high latitudes, slowing and turning equatorward as the signal moved to lower latitudes. This was fast, much faster than ionospheric winds, faster than most magnetospheric convection, but consistent with alpha wave propagation in the low-density plasma of the magnetosphere. Alpha waves are fundamental to magnetospheric dynamics. They carry energy and momentum along magnetic field lines, mediating interactions between different regions. When the solar wind impacts the magnetosphere, alpha waves carry the disturbance inward, coupling the outer magnetosphere to the ionosphere in seconds to minutes. The propagation speed depends on the magnetic field strength and plasma density, faster where the field is strong and the density is low, slower in denser regions. At ionospheric altitudes, around 100 to 300 kilometers above the surface, the alpha speed is typically a few hundred kilometers per second. Higher up, in the magnetosphere proper, it can exceed 1,000 kilometers per second. The observed propagation velocity of 1,500 kilometers per second suggested the disturbance was traveling through the outer magnetosphere or along field lines connecting the ionosphere to higher altitudes. But what initiated the wave? That was the question. Alpha waves in the magnetosphere are usually triggered by solar wind interactions. The solar wind is never perfectly steady. It contains turbulence, density variations, magnetic field rotations. These structures impact the magnetosphere continuously, generating waves that propagate inward. Most are small, contributing to the background noise level. Larger structures, like those associated with coronal mass ejections, produce major disturbances. But in mid-November 2024, the solar wind was quiet. No large structures had been observed upstream. The wave should not have been there, unless it came from somewhere else. Unless it was triggered not by the Sun, but by something between the Sun and Earth. Something like a comet's ion tail, 40 million kilometers away, creating a ripple in the interplanetary magnetic field that propagated inward, reached the magnetosphere, and coupled through the cusps to produce a brief, faint, measurable flicker in instruments scattered across the northern hemisphere. It was a long chain of causality, many links, many uncertainties. But the instruments had recorded something, and something had been happening in space at the time, and the coincidence was narrow enough to be intriguing. The magnetometers did not care. They continued sampling, second after second, measuring the field as it breathed and shifted, indifferent to interpretation. A comet is not a single object but a process. The nucleus, the solid core of ice and rock, is only the beginning. When far from the Sun, beyond the orbit of Jupiter, a comet is dormant. A dark, frozen lump a few kilometers across, its surface sculpted by radiation and micrometeorite impacts over the eons it has spent in the outer solar system, or, in the case of interstellar visitors, in the cold between stars. Surface temperatures hover near the temperature of the cosmic microwave background, about 3 Kelvin, barely above absolute zero. Nothing moves, nothing sublimates. The comet is dead, or sleeping, but as it falls inward, pulled by the Sun's gravity, or simply passing through on a hyperbolic trajectory, the Sun's light warms it. Not uniformly, the nucleus rotates. Different regions face the Sun at different times, but steadily. When the surface temperature rises above the sublimation point of the most volatile ices, the transformation begins. Water ice sublimation becomes significant around 150 to 180 Kelvin, depending on the comet's heliocentric distance and the intensity of solar radiation. Carbon dioxide sublimates at lower temperatures, around 80 Kelvin. Carbon monoxide, even lower, around 25 Kelvin. On an interstellar comet, which may have formed in a colder protoplanetary disk than solar system comets, the ice composition might be enriched in hypervolatiles, methane, ammonia, nitrogen, which sublimate at even lower temperatures. The gas escapes from the surface, driven by vapor pressure gradients. It does not leave quietly. The sublimating ice carries dust with it, small particles of silicate, carbon, organic compounds that were mixed with the ice when the comet formed. The gas expands into the vacuum of space, cooling adiabatically as it does. The Coma forms, a diffuse cloud of gas and dust that can grow to be larger than a planet. Though its density is far lower than any planetary atmosphere, lower than the best laboratory vacuums on Earth. Within the Coma, sunlight breaks apart molecules. Water molecules, H2O, are dissociated by ultraviolet photons, producing hydroxyl radicals, OH, and hydrogen atoms. Hydroxyl is then dissociated further, producing oxygen. These processes happen on timescales of hours to days. Other molecules, carbon monoxide, carbon dioxide, cyanogen, methane, undergo similar photodissociation, creating a complex chemistry of radicals and fragments. Some molecules and atoms are ionized, either by solar ultraviolet radiation or by charge exchange with the solar wind. Water molecules lose an electron and become H2O+. Hydroxyl becomes OH+. Carbon monoxide becomes CO+. These ions carry an electric charge, and charged particles respond to electromagnetic forces. This is where the interaction with the solar wind begins. The solar wind is a stream of charged particles, mostly protons and electrons, with a small admixture of heavier ions flowing outward from the Sun at hundreds of kilometers per second. It carries the Sun's magnetic field with it, frozen into the plasma by a principle called magnetic flux freezing. Where the plasma goes, the field follows. And where the field goes, the plasma follows. When the solar wind encounters a comet, the interaction depends on the comet's gas production rate. For a weakly active comet, the solar wind flows around the coma with only minor perturbation. For a highly active comet, the gas production is strong enough to create a bow shock, a standing wave in the solar wind where the flow abruptly slows and heats, much like the shock that forms in front of a supersonic aircraft. 3I/Atlas was somewhere in between. Its gas production rate, estimated from brightness measurements and modeling, was on the order of 1027 to 1028 molecules per second around perihelion. This is modest. Comet Hale-Bopp, for comparison, produced around 1030 molecules per second at its peak, but 1028 molecules per second is not negligible. It is enough to create a substantial coma, enough to produce visible tails, enough to perturb the solar wind locally. The ions produced in the coma are picked up by the solar wind's magnetic field. The process is called ion pickup, and it involves a transfer of momentum from the solar wind to the newly created ions. A freshly ionized molecule near the comet is initially at rest in the comet's reference frame, moving at the comet's orbital velocity, but the solar wind is moving much faster, hundreds of kilometers per second. The magnetic field embedded in the solar wind sweeps over the ion, and electromagnetic forces accelerate it. The acceleration is not instantaneous. The ion begins to gyrate around the magnetic field line, spiraling at the cyclotron frequency, which depends on the ion's charge and mass and the field strength. As it gyrates, it is also carried along with the solar wind flow. The trajectory is a helix, a corkscrew path that moves away from the comet at the solar wind velocity. But the pickup process extracts energy from the solar wind. The accelerated ions gain kinetic energy, and that energy must come from somewhere. It comes from the bulk flow of the solar wind itself. The solar wind slows slightly as it picks up cometary ions. Mass is loaded into the flow. Momentum is conserved, but distributed over a larger mass, so the velocity decreases. This creates a region of slower, denser, more turbulent solar wind downstream of the comet. The region is called the cometary plasma tail or ion tail, and it is distinct from the dust tail. The dust tail is made of solid particles following ballistic trajectories, curved because the particles are pushed by radiation pressure, but also pulled by gravity. The ion tail is made of charged particles following magnetic field lines, and it points almost exactly away from the Sun, straight and narrow, extending millions of kilometers. The ion tail is not uniform. It has structure, streamers, knots, disconnection events where the tail breaks off entirely and a new tail forms. These structures reflect variations in the solar wind, changes in the interplanetary magnetic field direction, instabilities in the plasma. Observations of cometary ion tails provide information about solar wind conditions that is difficult to obtain otherwise, especially far from Earth where few spacecraft monitor the solar wind directly. For 3I/Atlas, the ion tail was faint but present, Ground-based telescopes imaged it in emission lines from ionized carbon monoxide and water. The tail extended at least several million kilometers, possibly farther. Its brightness suggested an ion production rate consistent with the estimated gas production rate. The tail was relatively straight, indicating stable solar wind conditions during most of the comet's passage through the inner solar system. But plasma tails carry magnetic fields. The field is not generated by the comet itself. Comets do not have intrinsic magnetic fields, but is inherited from the solar wind. The interplanetary magnetic field drapes around the comet, wrapping the ion tail in a sheath of twisted field lines. Currents flow along these field lines, carried by the ions streaming away from the comet, and currents generate magnetic fields, fields that add to, or subtract from, the background interplanetary magnetic field, fields that create gradients, kinks, structures in the magnetic environment around the comet. When such structures propagate outward with the solar wind, they can travel large distances before dissipating. They interact with other plasma, with other magnetic structures. They generate waves. Could such a disturbance, originating from 3 I/Atlas's ion tail, have reached Earth? 40 million kilometers is a long way. The solar wind takes about a day to travel that distance at typical speeds. By the time any cometary plasma reached Earth's orbit, it would have been mixed and diluted beyond individual identification. But waves can propagate faster than the bulk flow. Alphen waves, in particular, travel at the alphen speed relative to the plasma, which means they can outrun the flow itself. The numbers were uncertain, the geometry complicated, but the possibility existed, faint and speculative, like the flicker itself. The mathematics of wave propagation in magnetized plasma is not simple. The equations are coupled, non-linear, and difficult to solve except in highly idealized cases. But certain principles are clear. Derived from magnetohydrodynamics, the physics of electrically conducting fluids in magnetic fields, a framework developed in the mid-20th century to understand plasmas in stars, in fusion reactors, in planetary magnetospheres. One fundamental result is the existence of wave modes, distinct types of oscillations that can propagate through plasma, each with characteristic properties. The 3 primary modes in magnetohydrodynamics are the MAVEN wave, the fast magnetosonic wave, and the slow magnetosonic wave. The MAVEN wave is an oscillation in the magnetic field and plasma velocity perpendicular to the background field direction. It propagates along field lines at the MAVEN speed, which is given by the square root of the magnetic field strength divided by the plasma mass density, multiplied by a constant. In the solar wind near Earth's orbit, where the magnetic field is a few nanoteslas and the plasma density is a few particles per cubic centimeter, the MAVEN speed is typically between 50 and 100 kilometers per second. Farther from the Sun, where the density is lower, the MAVEN speed can be higher. The fast magnetosonic wave is a compressional wave, similar to a sound wave, but modified by the presence of the magnetic field. It propagates in all directions, not just along field lines, and its speed depends on both the MAVEN speed and the sound speed in the plasma. In the solar wind, the fast mode speed is comparable to or slightly higher than the MAVEN speed. The slow magnetosonic wave also compresses the plasma, but it propagates only along field lines and at speeds slower than the MAVEN wave. When a disturbance occurs in the solar wind, a density enhancement, a magnetic field rotation, a current surge, it excites some combination of these wave modes. The waves propagate outward from the disturbance, carrying information and energy. The relative amplitudes of the different modes depend on the nature of the disturbance and the background plasma conditions. For a comet's ion tail, the disturbance is primarily magnetic. The pickup of ions creates currents, and currents modify the magnetic field. The draping of the interplanetary magnetic field around the Coma creates kinks and bends in the field lines. These are favorable conditions for generating MAVEN waves. But MAVEN waves are not the whole story. The interaction between the solar wind and cometary plasma is turbulent. Instabilities develop. Energy cascades from large scales to small scales, dissipating as heat. Some energy goes into accelerating particles to high velocities, creating energetic ions that escape the comet's vicinity entirely. Numerical simulations of comet-solar-wind interactions show complex, time-varying structures. Magnetic field lines pile up on the sunward side of the Coma, creating a magnetic barrier. The field strength can increase by factors of 2 to 5 compared to the undisturbed solar wind. Downstream, in the ion tail, the field is stretched and twisted. Waves propagate both upstream and downstream, interfering with each other, creating regions of enhanced and reduced field strength. These simulations are challenging to perform. They require solving the MHD equations, or more advanced kinetic equations that account for the discrete nature of particles, on grids with millions of cells, over many time steps. Even with powerful supercomputers, compromises must be made. Simplified geometries, reduced spatial resolution, assumptions about the comet's gas production rate and composition. But the simulations provide insight. They show that disturbances from cometary plasma can propagate large distances. They show that the disturbance is not confined to the immediate vicinity of the comet, but spreads laterally and longitudinally, carried by the solar wind and by wave propagation. For 3I/Atlas. No dedicated simulations were run at the time of its passage. The comet was not expected to be particularly remarkable. Its trajectory did not bring it close to any spacecraft that could provide in situ measurements. Observations were largely optical and spectroscopic, focused on characterizing the comet's composition and activity level, not its plasma interactions. But generic simulations of comet-solar wind interactions could be applied, at least qualitatively. They suggested that the ion tail would create a wake in the solar wind extending tens of millions of kilometers downstream. Within this wake, the magnetic field would be perturbed, not dramatically, but measurably. Field rotations on the order of 10 to 30 degrees, density enhancements of 10 to 50%, MAVEN waves with periods ranging from minutes to hours. If such a wake happened to cross Earth's orbit, and if the timing was such that Earth passed through it shortly after, the magnetosphere might respond. The keyword is might. The magnetosphere does not respond equally to all solar wind disturbances. Some structures couple efficiently to the magnetosphere, driving strong geomagnetic activity. Others pass by with little effect. The efficiency of coupling depends on the orientation of the interplanetary magnetic field. When the field points southward, opposite to Earth's northward-pointing magnetic field at the equator, magnetic reconnection occurs at the day-side magnetopause. Reconnection is a process where oppositely directed magnetic field lines break and reconnect in a new configuration, releasing energy and allowing solar wind plasma to enter the magnetosphere. This drives geomagnetic storms, auroras, magnetic substorms. When the interplanetary magnetic field points northward, coupling is much weaker. Reconnection still occurs, but at higher latitudes, in the lobes of the magnetotail, and the energy input to the magnetosphere is reduced. Geomagnetic activity is low. In mid-November 2024, around the time of 3I/Atlas's closest approach to Earth, the interplanetary magnetic field was predominantly northward or weakly oriented. This was not favorable for strong magnetospheric coupling, but the flicker was not a strong disturbance. It was faint. Perhaps it did not require strong coupling. Perhaps a brief, localized rotation of the interplanetary magnetic field, a kink propagating as an MAVEN wave, was enough to trigger a weak, transient response in the high-latitude ionosphere. The propagation time could be estimated 40 million kilometers, divided by the alpha speed in the solar wind, say 80 kilometers per second, gives about 5.5 days. 3I/Atlas reached its closest approach to Earth on November 14th. 5.5 days later would be November 19th or 20th. But the magnetometer anomaly occurred on November 15th. The timing did not match, unless the alpha speed was higher than average, or unless the disturbance was not carried by an MAVEN wave alone, but by a fast magnetosonic wave, which travels faster, or unless the geometry was different, the comet's wake not intersecting Earth directly, but passing nearby, close enough that lateral propagation of waves could reach the magnetosphere, or unless the correlation was coincidental. The uncertainties multiplied. Each step in the chain of reasoning required assumptions, estimates, approximations. The result was not a proof, but a hypothesis, tentative and fragile. Still, it was something to consider, something to model, to test, to search for in future data when the next interstellar comet arrives. Magnetometers do not exist in isolation. They are part of networks, systems designed to monitor Earth's magnetic field globally, to provide data for scientific research, for space weather forecasting, for navigation, for studies of the deep Earth. The networks have names, acronyms that compress institutional histories and international collaborations into a few letters: Intermagnet, Supermag, Image, Themis, Charisma, Intermagnet. The International Real-Time Magnetic Observatory Network is perhaps the most established. It began in the 1980s as an effort to coordinate geomagnetic observatories around the world, to standardize data formats, to ensure data quality, and to make data available rapidly for operational use. Today, Intermagnet includes more than 100 observatories distributed across all continents and many oceanic islands. Each observatory operates continuously, collecting data at 1 second or 1 minute cadence, transmitting the data to regional data centers, which then distribute it to the global community. The observatories are permanent installations. Concrete piers anchor the magnetometers to bedrock, minimizing vibration. Temperature-controlled shelters house the electronics. Absolute instruments, proton precession magnetometers, overhauser magnetometers provide reference measurements to detect and correct drift in the fluxgate sensors. The data are reviewed by trained operators who flag anomalies, remove spikes caused by local interference, and ensure that the records are as clean as possible. Supermag takes a different approach. Instead of operating observatories directly, Supermag collects data from existing networks, Intermagnet, National Magnetometer Arrays, university-operated stations, and combines them into a single, unified data set. The data are reprocessed to remove baseline offsets, to align different coordinate systems, to apply corrections for external currents. The result is a dataset with more than 500 stations, far denser spatial coverage than any single network, ideal for studying the global structure of geomagnetic disturbances. Other networks focus on specific regions or phenomena. Image, the International Monitor for Auroral Geomagnetic Effects, consists of magnetometers in Scandinavia and the Arctic, designed to study auroral currents and substorms. Themis, time, history of events and macroscale interactions during substorms, includes ground-based magnetometers in North America aligned with spacecraft orbits, enabling coordinated space-ground observations. Charisma, Canadian Array for Real-Time Investigations of Magnetic Activity, provides dense coverage across Canada. Together, these networks form a global observing system. When a geomagnetic disturbance occurs, it is seen simultaneously by dozens or hundreds of stations. The spatial pattern can be mapped, the temporal evolution can be tracked, the source region can be inferred, but combining data from multiple networks is not trivial. Each network has its own data format, coordinate system, calibration procedures, Some stations report magnetic field components in geographic coordinates, others in geomagnetic coordinates. Some apply digital filters to reduce noise, others do not. Sampling rates vary. Data gaps occur when instruments fail or when communication links are interrupted. Researchers who use multi-network data must account for these inconsistencies. They apply transformations to align coordinate systems. They interpolate over small data gaps. They average or resample data to a common cadence. They calculate indices, derived quantities that summarize certain aspects of geomagnetic activity to facilitate comparison across different events and different studies. One widely used index is Kp, a quasi-logarithmic measure of geomagnetic disturbance based on data from a specific set of mid-latitude observatories. Kp ranges from 0, very quiet, to 9, extreme storm. It is updated every 3 hours, providing a coarse but globally representative measure of activity. During major geomagnetic storms, Kp can reach 8 or 9. During quiet periods, it hovers around 0 to 2. Another index is distate, which measures the strength of the ring current, a westward flowing current of energetic particles that encircles Earth during geomagnetic storms. Dist is calculated from low-latitude magnetometer stations and is expressed in nanoteslas. During quiet times, Dist is near 0. During storms, it drops to negative values, sometimes below -100 nt for moderate storms or below -250 nt for intense storms. The AE index measures auroral electrojet activity, currents flowing in the ionosphere at high latitudes during substorms. It is calculated from a network of stations distributed around the auroral oval. High AE values indicate strong auroral activity, often associated with bright auroras and rapid magnetic variations. On November 15, 2024, when the magnetometer flicker occurred, Kp was 1, Dist was near 0, perhaps -5 nt, AE was below 100 nt. All indices indicated quiet conditions, no significant geomagnetic activity, nothing that would normally warrant attention. This made the flicker more puzzling. If the indices showed quiet conditions, where did the disturbance come from? Indices are global averages. By design, they smooth over localized or brief variations. A disturbance lasting only a few minutes, affecting only high-latitude stations, might not significantly alter the 3-hourly Kp index. It might cause a small uptick in AE, but if the baseline is already low, the uptick might not be noticeable in the context of normal variability. This is a limitation of indices. They are useful for characterizing large-scale, long-duration events, but they can miss small, transient, localized phenomena. The flicker was exactly the kind of event that would slip through index-based monitoring. Finding it required going back to the raw magnetometer data, station by station, applying statistical techniques to identify coherent variations that were too small to trigger automated alerts, but too organized to be random noise. The technique used was called superposed epoch analysis. Researchers selected a time window around the suspected event, say 1 hour before to 1 hour after, and extracted data from all available stations. They then averaged the data, aligning the time series so that the disturbance on set at each station occurred at the same relative time. Random noise, being uncorrelated across stations, averaged towards 0. Coherent signals, present at multiple stations, reinforced each other and emerged clearly. The result was a clean signal, a small but distinct variation, consistent across the network, propagating from high to low latitudes over about 15 minutes. The superposed epoch analysis removed doubt about whether the flicker was real. It was there in the data, reproducible, measurable. But identifying a signal is not the same as explaining it. The next step was to search for other examples. If cometary plasma could perturb Earth's magnetosphere, perhaps it had happened before and gone unnoticed. Historical magnetometer data extend back decades. Comets pass through the inner solar system regularly, several per year, though most are faint and poorly observed. A search was conducted. Researchers compiled a list of comets that had passed within 50 million kilometers of Earth over the past 20 years. They identified the dates of closest approach and extracted magnetometer data from those periods. They applied the same superposed epoch analysis, looking for coherent variations similar to the November 2024 flicker. The results were inconclusive. A few events showed small variations that might have been related to comets, but the signals were weak and ambiguous. Most comets produced no detectable signature at all. The only relatively clear case was 3I/Atlas. This was not surprising. Most comets are not particularly active when far from the Sun, and most pass Earth at distances where any plasma interaction would be negligible. 3I/Atlas was somewhat unusual in being fairly active, producing a visible coma and tail, and passing at a distance that was large in absolute terms, but small enough that, if the geometry and timing aligned properly, an interaction might just barely be possible. It was also possible that 3I/Atlas was a fluke. One event, one correlation. Insufficient for establishing causation. The scientific method requires reproducibility. A phenomenon observed once might be real, but it might also be an artifact, a coincidence, an error. To establish that comets can perturb Earth's magnetic field, one would need multiple clear examples, preferably with independent confirmation from other types of observations, so the conclusion, for now, was uncertain. The magnetometer data showed a real, coherent disturbance. The timing and location were suggestive of a connection to 3I/Atlas, but the physical mechanism was unclear, the propagation path uncertain, and the statistical significance marginal. Papers were drafted, cautiously worded, abstracts were submitted to conferences. The work was presented, discussed, critiqued. Some researchers found it intriguing, others were skeptical. The debate was polite, technical, free of drama. This is how science proceeds when the data are ambiguous, slowly, carefully, without rushing to conclusions. Meanwhile, the magnetometer networks continued their work. Data accumulated. New stations came online. Old stations were upgraded. The global coverage improved. The temporal resolution increased. The data quality refined. And somewhere in interstellar space, other comets drifted sunward, decades or centuries from arrival, carrying ice and dust and perhaps the potential to leave faint, fleeting traces in the magnetic records of a distant planet. The data, when examined closely, revealed details that complicated the narrative. The flicker was not a single, uniform pulse but had structure, variations from station to station that hinted at underlying complexity. At alert, the northernmost station, the disturbance began at 3 hours 14 minutes and 37 seconds UTC, marked by a gradual increase in the northward magnetic field component. The increase was smooth at first, rising at about 0.15 nanoteslas per minute, then steepening slightly before plateauing at a peak amplitude of 0.68 nanoteslas above the background level. The plateau lasted approximately 2 minutes, then the field declined, returning to background levels by 3 hours 18 minutes and 45 seconds UTC. Total duration, 4 minutes and 8 seconds. The vertical and eastward components showed smaller variations, less than 0.2 nanoteslas, possibly within the noise level, difficult to interpret with confidence. At Tromsø, 3,200 kilometers southeast of Alert, and 3 minutes later, the signature was different. The northward component again showed an increase, but the rise was more abrupt, reaching a peak of 0.52 nanoteslas in about 90 seconds, followed by a slow decay. The duration was shorter, about 3.5 minutes. The eastward component showed a distinct variation, a brief decrease of about 0.3 nanoteslas coinciding with the northward increase, suggesting a rotation of the horizontal field vector. At Sodankila, another 650 kilometers east and 1 minute later still, the amplitude was smaller, 0.41 nanoteslas, but the shape was similar to Tromsø. The eastward component variation was more pronounced, nearly 0.4 nanoteslas, indicating a stronger rotation. At mid-latitude stations like Ottawa and Uppsala, the signal weakened further. The northward component variations were barely above the noise threshold, around 0.3 nanoteslas, and required averaging over multiple 1-second samples to identify clearly. The duration shortened to 2 minutes or less. The eastward component variations were inconsistent, present at some stations and absent at others. At low latitude and equatorial stations, no coherent signal could be identified. The magnetometer traces looked like typical quiet day variations, dominated by the solar quiet current system and random fluctuations. This spatial pattern, strong at high latitudes, weak at mid-latitudes, absent at low latitudes, was consistent with a disturbance entering through the polar cusps and propagating equatorward along ionospheric current paths. The cusps are regions near the magnetic poles where Earth's magnetic field lines connect directly to the interplanetary magnetic field, allowing solar wind particles and electromagnetic disturbances to penetrate more easily into the Magnetosphere ionosphere system. The temporal pattern, appearing first at one high-latitude station, then propagating to others over several minutes, suggested a wave-like disturbance moving through the ionosphere or along magnetospheric field lines. The propagation velocity, estimated from the time delays between stations and their geographic separations, was approximately 1,500 kilometers per second at high latitudes, decreasing to around 800 kilometers per second at mid-latitudes. These velocities were consistent with Alphen waves propagating along magnetic field lines in the magnetosphere. The Alphen speed depends on the magnetic field strength and plasma density, both of which vary with altitude and latitude. At ionospheric altitudes, where the plasma density is relatively high, the Alphen speed is a few hundred kilometers per second. At higher altitudes, in the low-density regions of the outer magnetosphere, the Alphen speed can exceed 1,000 kilometers per second. A disturbance entering through the cusp would propagate both downward along field lines toward the ionosphere and horizontally along the auroral oval, carried by ionospheric currents and magnetospheric waves. The downward propagation would be faster, reaching the ionosphere in seconds. The horizontal propagation would be slower, taking minutes to cover thousands of kilometers. This matched the observations. The flicker appeared first at the station closest to the magnetic cusp, then spread to other high-latitude stations, then propagated equatorward as the disturbance coupled to lower-latitude field lines. But what triggered the disturbance at the cusp? Normally, cusp dynamics are driven by the solar wind. When the interplanetary magnetic field has a southward component, reconnection occurs at the dayside magnetopause, and newly reconnected field lines are dragged over the polar cap toward the night side, threading through the cusp region and creating characteristic ion and electron precipitation patterns. Ground-based radars and all-sky cameras can observe these patterns, providing information about the reconnection rate and the solar wind conditions. But on November 15, 2024, the IMF was predominantly northward. Reconnection was likely occurring in the lobes, not at the dayside magnetopause. Cusp activity should have been minimal. Yet the magnetometer flicker suggested that something had perturbed the cusp. A brief, localized disturbance, too small to create visible auroras or strong radar signatures, but enough to generate the small magnetic variations recorded at ground stations. One possibility was a transient structure in the solar wind, a discontinuity, a rotational change in the IMF direction, or a density pulse. Such structures occur frequently, embedded in the turbulent solar wind. Most pass by without noticeable effects, but occasionally one arrives with the right geometry to couple briefly to the magnetosphere, creating a transient response. Spacecraft data from the L1 Lagrange point, about 1.5 million kilometers upstream of Earth, were examined. L1 hosts several satellites that monitor the solar wind continuously: ACE, WIND, DSCOVAR. These spacecraft measure the solar wind velocity, density, temperature, magnetic field, and energetic particle fluxes with high time resolution. The data from November 15th, around the time that any solar wind disturbance would have passed L1 before reaching Earth, accounting for the propagation time of about 45 to 60 minutes at typical solar wind speeds, showed nothing remarkable. The solar wind speed was 385 kilometers per second, slow and steady. The density was 2 protons per cubic centimeter, typical. The magnetic field strength was 4.8 nanoteslas, unremarkable. The field direction was primarily northward, BAS component around +3 nt with small fluctuations. There were no sharp discontinuities, no sudden density jumps, no large field rotations. The solar wind was quiet, as the indices had indicated. This was a problem for the hypothesis. If the flicker was caused by a solar wind disturbance reaching the magnetosphere through the cusps, that disturbance should have been visible in the upstream solar wind data. But it was not there. Which left two possibilities. Either the disturbance was too small or too brief to be resolved by the spacecraft instruments, or it did not come from the solar wind at all. The first possibility could not be entirely ruled out. The spacecraft at L1 are point measurements. They sample the solar wind at a single location. If a small, localized structure passed between the spacecraft or at a slightly different solar longitude, it might have missed the spacecraft entirely, but still reached Earth. The solar wind is not perfectly homogeneous. It has structure on many scales, but this seemed unlikely. The magnetometer flicker affected a broad latitudinal range, suggesting a disturbance that was not highly localized. A solar wind structure large enough to produce such a widespread response should have been detectable by at least one of the spacecraft, which brought the focus back to the second possibility. The disturbance did not originate from the solar wind in the usual sense, but from something else, something that perturbed the interplanetary magnetic field at a location between the Sun and Earth, sending waves or currents propagating outward, reaching the magnetosphere from a direction or with a signature that was unusual, unexpected, something like a comet's plasma tail. The geometry was checked again. On November 14th, 3I/Atlas was 40 million kilometers from Earth, roughly in the direction of the Sun, but slightly off to one side. The comet's ion tail pointed away from the Sun, which meant it pointed generally toward the outer solar system, away from Earth. The tail was not aimed at Earth. But plasma tails are not rigid structures. They wave, they kink, they bend in response to variations in the solar wind and the interplanetary magnetic field. Disconnection events occur, where the tail breaks off and drifts away while a new tail forms. Magnetic field lines thread through the tail in complex patterns. If a kink or wave in the tail happened to propagate laterally, or if the tail's magnetic signature created disturbances in the surrounding solar wind that then propagated to Earth, the geometry might allow an interaction even though the tail itself was not pointed at Earth. It was speculative. It required a specific set of circumstances to align, but it was not impossible. And in the absence of any other explanation, it remained on the table. The ionosphere is not passive. It is not merely a layer of rarefied atmosphere where ultraviolet radiation from the Sun strips electrons from atoms and creates a weakly ionized plasma. It is dynamic, structured, constantly responding to forces from above and below. From above, the solar wind and magnetosphere impose electric fields and currents. From below, atmospheric waves propagate upward from the lower atmosphere, carrying energy and momentum. The ionosphere mediates these interactions, coupling the neutral atmosphere to the magnetized plasma environment of near-Earth space. The coupling occurs through several mechanisms. One is conductivity. Ionospheric plasma conducts electricity, though not uniformly. The conductivity depends on the ion and electron densities, the collision frequency with neutral atoms, and the strength and direction of the magnetic field. At high latitudes, where magnetic field lines are nearly vertical, the plasma can move relatively freely along field lines, but is inhibited from moving across them. This creates anisotropic conductivity, different conductivities parallel and perpendicular to the magnetic field. Two types of conductivity are particularly important: Pedersen conductivity and Hall conductivity. Pedersen conductivity describes current flow in the direction of the applied electric field. Hall conductivity describes current flow perpendicular to both the electric field and the magnetic field. Both are functions of altitude, reaching maximum values around 120 to 150 kilometers, where the ion-neutral collision frequency and the ionization density are both significant. When electric fields are imposed on the ionosphere, for example, by the magnetosphere mapping electric potentials down magnetic field lines, currents flow. These currents are confined primarily to the E region of the ionosphere, between about 90 and 150 kilometers altitude, where the conductivity is highest. The currents form coherent structures, the auroral electrojets, flowing eastward and westward along the auroral oval, the polar cap currents, flowing across the polar cap from the day side to the night side, the equatorial electrojet, flowing eastward along the magnetic equator. These currents generate magnetic fields that can be detected at the ground. This is, in fact, what magnetometers measure during geomagnetic disturbances, not the magnetospheric currents directly, which are too far away, but the ionospheric currents they drive, which flow only 100 to 200 kilometers above the surface. The relationship between ionospheric currents and ground magnetic variations is governed by the geometry and distribution of the currents. A horizontal current sheet flowing at ionospheric altitude produces a magnetic perturbation at the ground that points perpendicular to the current direction, with strength proportional to the current density and inversely proportional to the distance from the current. This is described by Ampere's law, one of Maxwell's equations, relating magnetic fields to the currents that produce them. For the November 15th flicker, the ground magnetic variations suggested a horizontal current flowing in the ionosphere, oriented roughly east-west, with current density varying over time and space. The northward magnetic component variations implied an eastward current during the main phase of the disturbance, diminishing as the disturbance passed. But what drove the current? Ionospheric currents are driven by electric fields. In the magnetosphere-ionosphere system, electric fields can be imposed by several mechanisms. During substorms, the reconfiguration of the magnetotail creates electric fields that map down to the ionosphere and drive the auroral electrojets. During steady magnetospheric convection, the electric field associated with the large-scale circulation of plasma in the magnetosphere maps to the ionosphere and drives polar cap currents. For a transient, localized disturbance like the flicker, the most likely driver was a brief pulse of electric field, perhaps associated with a transient change in the magnetospheric configuration. One hypothesis was ionospheric-magnetospheric coupling via MAVEN waves. If a disturbance in the interplanetary medium, such as a kink in the magnetic field associated with cometary plasma, reached the magnetopores and coupled into the magnetosphere, it could excite MAVEN waves that propagated along field lines. These waves carry electric and magnetic field perturbations. When they reach the ionosphere, They drive currents through the pedicin and Hall conductivities. The currents, in turn, generate magnetic perturbations observable at the ground. This mechanism is well established for solar wind-driven disturbances. Sudden impulses in the solar wind, sharp increases in dynamic pressure, create compressional waves in the magnetosphere that propagate to the ionosphere and generate brief magnetic variations called sudden commencements. These are global phenomena seen at magnetometer stations worldwide, with characteristic signatures that depend on local time and latitude. The November 15th flicker was not a sudden commencement. It was too small, too localized, and not associated with any detected pressure pulse in the solar wind. But the underlying physics might be similar: a disturbance entering the magnetosphere, exciting waves, driving ionospheric currents, producing ground magnetic variations. The key question remained: what was the source of the disturbance? If it came from the comet, the pathway would have been indirect. The comet's plasma tail, interacting with the solar wind, would create magnetic field perturbations. These perturbations, carried by the solar wind or propagating as waves, would reach the vicinity of Earth. If the geometry and timing were right, the perturbations could couple to the magnetosphere through the cusps or through the flanks of the magnetosphere, where the field lines are more easily influenced by external disturbances. The coupling would not be efficient. Most of the energy in the perturbation would flow past Earth, carried downstream by the solar wind. Only a small fraction would couple into the magnetosphere. But a small fraction of a large disturbance, or a more efficient coupling of a smaller disturbance, might be enough to drive a transient current in the ionosphere, lasting a few minutes, creating a 0.5 nanotesla magnetic variation at the ground. Numerical simulations could test this hypothesis. Global magnetohydrodynamic models of the magnetosphere exist, capable of simulating the response to specified solar wind conditions. One could input a model of the interplanetary magnetic field perturbed by cometary plasma, run the simulation, and see whether the modeled magnetosphere produces ionospheric currents consistent with the observed ground magnetic variations. Such simulations are computationally expensive and require detailed knowledge of the input conditions. For the November 2024 event, the comet's plasma properties were not measured directly. No spacecraft flew through the coma or tail. The ion production rate, the tail geometry, the magnetic field structure in the tail, all were inferred from remote observations and theoretical models, with significant uncertainties. Still, a simulation could provide a plausibility check. If the simulation produced no significant ionospheric response, even under optimistic assumptions about the comet's plasma output, the hypothesis could be ruled out. If the simulation did produce a response, it would not prove causation, but it would strengthen the case. To date, no such simulation has been published. The resources required and the uncertainty of the result have not yet justified the effort for a single, ambiguous event. So the ionospheric coupling hypothesis remains just that, a hypothesis, plausible but unproven, awaiting either more data from future comets or a dedicated modeling effort. The ionosphere continues its work, conducting currents, coupling the magnetosphere to the ground, indifferent to whether the currents are driven by familiar solar wind structures or by something more unusual. Science advances unevenly. Some questions yield to sustained effort, data accumulation, and theoretical refinement. Others remain stubbornly resistant, hedged by uncertainties, limited by sparse observations, trapped in the gap between what is measurable and what is meaningful. The question of whether 3I/Atlas perturbed Earth's magnetic field sits in that gap. The evidence is suggestive but not conclusive. A small, coherent magnetic disturbance occurred at a time when an interstellar comet was passing at a distance where direct interaction should have been negligible, but where indirect effects, via plasma and magnetic field perturbations propagating through the interplanetary medium, were not impossible. The disturbance had characteristics consistent with a transient coupling to the magnetosphere through the polar cusps, driving brief ionospheric currents. But the solar wind was quiet, showing no obvious trigger, and the physical pathway from comet to magnetosphere remained speculative. In statistical terms, the event is a single data point. One comet, one flicker, one correlation. The probability of such a correlation occurring by chance is not negligible. Magnetometer data contain many small, transient variations. Comets pass through the inner solar system regularly. Given enough comets and enough time, coincidences will occur. To establish causation, one needs either multiple events showing the same pattern, a statistical ensemble demonstrating that comet passages are systematically associated with magnetometer anomalies, or a single event with such clear, unambiguous signatures that coincidence can be ruled out. The November 2024 event provides neither. This is not a failure. It is the normal state of science at the boundary of knowledge. Anomalies are noticed. Hypotheses are proposed. Data are examined. Some hypotheses are ruled out. Others remain viable, waiting for better observations or new theoretical insights. The history of geophysics is full of such waiting. The existence of the magnetosphere itself was hypothesized in the 1930s by Chapman and Ferraro based on theoretical considerations of how solar plasma might interact with Earth's magnetic field. But it was not confirmed observationally until spacecraft measurements in the late 1950s and early 1960s. The geodynamo, the mechanism generating Earth's magnetic field, was proposed in the 1940s. But a quantitative, self-consistent model was not achieved until the 1990s, and many details remain uncertain. Magnetic reconnection. Now understood to be a fundamental process in magnetospheric dynamics, was met with skepticism for decades after it was first proposed. The idea that magnetic field lines could break and reconnect seemed to violate the principle of flux freezing, which states that in highly conductive plasmas, magnetic field lines are tied to the plasma and cannot change topology. It took careful observations from multiple spacecraft, combined with advances in plasma kinetic theory, to demonstrate that reconnection occurs in thin regions where the plasma is not perfectly conductive and where the magnetic field can diffuse through the plasma. The November 2024 flicker may eventually be understood as a manifestation of some physical process that is currently underappreciated or poorly modeled, or it may be revealed as coincidence once enough similar events are examined and no consistent pattern emerges. Either outcome would be scientifically valuable. Confirming a new coupling mechanism between comets and magnetospheres would expand understanding of how small, transient disturbances propagate through the heliosphere. Ruling it out would refine knowledge of what kinds of disturbances are large enough to matter and what kinds can be safely ignored. But obtaining that clarity requires more events, more interstellar comets, more high-quality magnetometer data, more coordinated observations. Interstellar comets are rare. Since 1I/Oumuamua in 2017, only 2 more have been confirmed as of late 2024, 2I/Borisov and 3I/Atlas. Estimates suggest that a few interstellar objects per year enter the inner solar system, but most are faint and difficult to detect. Improvements in survey telescopes, projects like LSST, the Legacy Survey of Space and Time now operating as the Vera C. Rubin Observatory, will increase the detection rate. Within a decade, dozens of interstellar objects may be catalogued. Each will be an opportunity. If future interstellar comets show similar magnetometer anomalies when passing at comparable distances, the hypothesis will gain support. If they do not, the November 2024 event will be relegated to a footnote, an unexplained curiosity in the archive. Science is patient, the data accumulate slowly. The instruments keep measuring, second by second. The networks keep operating. Year by year, The archives grow. Somewhere in those archives, in the magnetometer records from 1950 onward, there may be other faint, unexplained flickers, other transient disturbances that were too small to trigger alerts, too brief to be noticed during routine analysis, but present nonetheless. Mining those archives, applying modern statistical techniques, looking for patterns across decades, could reveal whether the November 2024 event was unique or part of a larger pattern. Such work is laborious. It requires processing terabytes of data, accounting for changes in instrumentation and data formats over decades, separating genuine geophysical signals from artifacts and noise. But it is feasible, and it is being done slowly, by researchers with patience and computational resources. Until those analyses are complete, the question remains open. The silence of statistical significance is not the same as absence. It is simply waiting. The other interstellar visitors left fewer questions, or at least different ones. 1I/Oumuamua arrived first. In October 2017, detected by the Pan-STARRS 1 telescope as a faint, fast-moving object on a clearly hyperbolic orbit. It passed closest to the Sun on September 9, 2017, at a distance of 0.25 AU, inside Mercury's orbit, and closest to Earth on October 14 at about 0.16 AU, roughly 24 million kilometers. It was observed for several weeks before fading beyond detection limits as it raced back toward interstellar space at a speed exceeding 26 kilometers per second relative to the Sun. Its shape was inferred from the unusual variation in its brightness as it rotated. The light curve, the plot of brightness versus time, showed large variations, suggesting either a highly elongated shape or extreme surface albedo differences. Most models favored an elongated shape, possibly 200 meters long and only 30 meters wide. Though the exact dimensions remain debated, it showed no visible coma or tail despite passing close enough to the Sun that ices should have sublimated. Either it was not icy, perhaps a rocky or metallic object, or it had lost its volatiles long ago during previous close encounters with other stars, or the ices were buried beneath a thick, radiation-darkened crust. Most intriguingly, Oumuamua exhibited a small, non-gravitational acceleration as it left the inner solar system. The acceleration was directed away from the Sun, suggesting outgassing, sublimating ices pushing the object like a rocket, but no gas was detected. Alternative explanations included radiation pressure acting on a thin, sail-like shape, or outgassing of a volatile with no observable spectral signature, like molecular hydrogen or nitrogen. No one checked for magnetometer anomalies associated with Oumuamua. It was not expected to produce plasma, and no one was thinking about comet magnetosphere interactions for an object that showed no cometary activity. 2I/Borisov was different. Discovered in August 2019, it was clearly a comet from the start. With a visible coma and spectroscopic detection of outgassing, it passed perihelion on December 8, 2019 at a distance of 2.0 AU, well outside Earth's orbit, near the asteroid belt. Its closest approach to Earth was about 1.9 AU, roughly 290 million kilometers, far too distant for any plausible interaction with the magnetosphere. Extensive observations characterized its composition: water vapor, carbon monoxide at unusually high abundance relative to water, cyanogen, dust. The coma and tail were typical of active comets. Its nucleus size was estimated at around 0.4 to 1 kilometer across, though, as with all comets, the uncertainty is large because the nucleus is hidden within the coma. Again, no magnetometer anomalies were reported, but the distance was too great for any to be expected. 3I/Atlas, discovered in June 2024, fell between these two. It was clearly active, with a coma and tail, like Borisov. But its closest approach to Earth, 40 million kilometers, was much closer than Borisov's, though still far compared to Oumuamua's. 3 interstellar objects, 3 different outcomes. Oumuamua, mysterious, inactive or appearing inactive, passing close to Earth but producing no obvious magnetospheric effects. Borisov, clearly cometary, well studied, but passing too far away to matter for magnetospheric interactions. 3 I/Atlas, active, at an intermediate distance, possibly associated with a faint magnetometer flicker. The sample size is too small for generalizations. Each object is unique. The conditions during their passages, solar wind state, magnetospheric configuration, Earth's position relative to the object's trajectory, were all different, but a pattern might eventually emerge. If 5 or 10 interstellar comets are observed in the next decade, and if some fraction of them show similar magnetometer anomalies when they pass within a certain distance range, that would be compelling. If none show such anomalies, it would suggest that the November 2024 event was either a false positive or an exceptionally rare alignment of circumstances. The waiting continues. Astronomers scan the sky. New objects appear in the data. Most are asteroids or comets from the Kuiper belt or Oort cloud, gravitationally bound to the Sun. Occasionally, an orbit calculation yields an eccentricity greater than 1, and excitement builds, another interstellar visitor. Each one is studied intensively. Spectroscopy, photometry, astrometry to refine the orbit, observations in multiple wavelengths, visible, infrared, radio, searches for variability, for outgassing, for unusual composition. The observations are archived, made publicly available, analyzed and reanalyzed by researchers around the world. And now, perhaps, future studies will include checks of magnetometer data, a new item on the checklist. When an interstellar comet passes within some critical distance of Earth, examine the magnetometer records for small, transient, high-latitude disturbances. If the check becomes routine, if it is performed for every interstellar visitor, the question will eventually be answered. Either the pattern will appear, or it will not. This is how science builds knowledge, one observation at a time, one hypothesis tested, one null result or one confirmation, accumulating over years and decades until the picture becomes clear. Stone remembers, not in the way living tissue remembers, encoding experience in neural connections, subject to revision and forgetting. Stone remembers with fidelity, inscribing the conditions of its formation in mineral structures that persist for billions of years, until erosion grinds them to sand or subduction melts them back into the mantle. Magnetic minerals, magnetite, hematite, titanohematite, magamite, are among the most faithful recorders. When molten rock cools below the Curie temperature, the temperature at which magnetic ordering becomes stable, magnetic domains within the crystals align with the ambient magnetic field. As the rock continues to cool, this alignment is locked in, frozen into the crystal lattice. The rock becomes a permanent magnet, weak but persistent, carrying a record of the field direction and intensity at the time and place of its formation. This is called thermo-remanent magnetization, and it is the basis of paleomagnetism. Sedimentary rocks acquire magnetization differently. As sediment settles in water, magnetic grains align with the ambient field like tiny compass needles. When the sediment lithifies, compacts and cements into solid rock, the alignment is preserved. This detrital remanent magnetization is generally weaker and less reliable than thermo-manent magnetization, but in quiet depositional environments, it can preserve useful field information. By measuring the magnetization of rocks of different ages, scientists reconstruct the history of Earth's magnetic field. The direction of magnetization indicates the direction the field pointed when the rock formed. The intensity of magnetization, if calibrated carefully, indicates the field strength. The record extends back billions of years. Rocks from Western Australia, dated to 3.5 billion years ago, carry magnetic signatures indicating that the geodynamo was active at that time. The field was weaker than today, perhaps half the current strength, but it was present. This is important. Without a magnetic field, Earth might have lost its atmosphere to solar wind erosion. Mars lost its global magnetic field early, perhaps within the first few 100 million years of its history, and subsequently lost most of its atmosphere. The Martian surface today is a cold, desiccated desert with an atmospheric pressure less than 1% of Earth's. Earth kept its field and therefore kept its atmosphere, and therefore provided conditions where liquid water could persist on the surface for billions of years, where life could emerge and evolve, where complexity could accumulate. The paleomagnetic record also reveals reversals. Layers of rock formed during a reversed polarity interval have magnetization pointing opposite to the current field direction. Mapping these reversals in volcanic rocks and seafloor basalts has allowed construction of a geomagnetic polarity timescale extending back hundreds of millions of years. The pattern is irregular. Some polarity intervals last less than 100,000 years. Others last tens of millions of years. The Cretaceous normal superchron, for example, lasted about 40 million years without a reversal. The current normal polarity interval, the Brunhers-chron, has lasted 780,000 years, which is not particularly long by historical standards, but is long enough that some researchers speculate a reversal may be overdue. But the geodynamo does not follow a schedule. The irregularity of reversals suggests that they are triggered by chaotic dynamics in the core, not by external forcing or periodic processes. Predicting the next reversal is impossible with current understanding. During a reversal, the field weakens and becomes more complex. The dipole component, the dominant part of the field today, diminishes, and higher-order multipoles become more prominent. Multiple magnetic poles appear at the surface. The field geometry resembles a patchwork rather than a simple bar magnet. The weakened field provides less shielding from cosmic rays and solar particles, which may have biological or atmospheric consequences, though the magnitude of these effects is debated. Paleomagnetic studies have also identified brief, rapid field excursions, events where the field direction or intensity change dramatically over a few centuries or millennia, then return to normal without completing a full reversal. The Laschon excursion, about 41,000 years ago, saw the field intensity drop to about 25% of its normal value and the dipole axis tilt significantly. The excursion lasted about 1,000 years. Such excursions are less well understood than full reversals. They may represent failed reversal attempts, instabilities in the core flow that did not culminate in a complete field reversal, or they may be distinct phenomena, driven by different dynamics. The paleomagnetic record is also sensitive to other processes. Variations in field intensity on timescales of decades to centuries have been detected, associated with changes in core flow patterns. These are called geomagnetic jerks and secular variation, gradual, ongoing changes in field strength and direction that occur even during stable polarity intervals. What the paleomagnetic record does not preserve, however, are brief, small amplitude variations like the November 2024 flicker, a disturbance lasting a few minutes, with amplitude less than 1 nanotesla, leaves no trace in rock. The magnetization process requires time, hours to cool through the Curie temperature for volcanic rocks, years or centuries for sediments to accumulate and lithify. Transient events are smoothed away, averaged out, lost to the geologic record. This means that if cometary passages have been perturbing Earth's magnetic field throughout history, creating small Brief flickers like the one possibly associated with 3I/Atlas, there would be no paleomagnetic evidence. The phenomenon could have occurred millions of times over billions of years and left no fossil signature. Stone remembers the long and the slow. It remembers polarity reversals, excursions, the gradual drift of the magnetic poles over centuries. It remembers the field strength averaged over millennia, but it does not remember individual geomagnetic storms, or substorms, or the passage of comets. For those, one needs instruments. Magnetometers that sample every second. Archives that preserve every measurement. Networks that operate continuously, year after year. Building datasets that capture variability on all accessible timescales. The instrumental record extends back only about 180 years, to the establishment of the first permanent magnetic observatories in the mid-19th century. Before that, there are scattered measurements, compass declinations recorded by navigators, magnetic inclination measurements by natural philosophers, but nothing systematic, nothing continuous. 180 years is a blink in geologic time. It is less than 1,000th of the current polarity interval, less than 1/1,000,000th of Earth's history. The geodynamo has been operating for billions of years, and humanity has been watching closely for only 180. In that brief window, much has been learned. The structure of the field is mapped in detail. The rate of change is monitored. Solar-wind interactions are understood, at least in broad terms. Space weather forecasting has become operational, providing warnings of geomagnetic storms that might disrupt power grids, satellite operations, and communications. But there are still mysteries, still processes that are not fully understood, still observations that do not fit neatly into existing models. The November 2024 flicker may be one such mystery, or it may be noise, coincidence, an artifact of over-interpretation. Time and more data will tell. Stone will not record the answer, but the magnetometers will. If anyone remembers to check, uncertainty is not a flaw in scientific knowledge, but a feature. It is the acknowledgement that measurement has limits, that models are approximations, that the natural world is more complex than any description of it. The uncertainty surrounding the November 2024 magnetometer flicker and its possible connection to 3I/Atlas exists at multiple levels. There is measurement uncertainty. Magnetometers are precise, but not perfect. The quoted accuracy for a typical observatory fluxgate magnetometer is about 0.1 nanoteslas. The flicker amplitude at most stations was only a few times this value, measurable, but not with high signal-to-noise ratio. Small variations in instrument calibration, temperature drift, or local magnetic noise could produce signals of similar amplitude. There is temporal uncertainty. The exact onset time of the disturbance at each station is difficult to determine when the signal rises gradually from background noise. Different analysis techniques, manual inspection, automated detection algorithms, cross-correlation methods yield slightly different onset times, differing by tens of seconds. These differences affect the calculated propagation velocity and the inferred source location. There is spatial uncertainty. Magnetometer stations are not uniformly distributed. There are clusters in North America, Europe, and parts of Asia, but large gaps exist over oceans and the southern hemisphere. The observed propagation pattern is constrained only by the stations that exist. A denser network might reveal more complex structure, or might show that the apparent propagation was an artifact of sparse sampling. There is physical uncertainty. The mechanisms by which cometary plasma might interact with the magnetosphere are not fully understood. Theoretical models exist, but they rely on simplifications and assumptions. The interaction depends on many variables: the comet's ion production rate, the solar wind conditions, the interplanetary magnetic field orientation, the magnetospheric state, most of which were not directly measured for the November 2024 event. There is statistical uncertainty. with only one clear example. It is impossible to assess whether the correlation between the comet passage and the magnetometer anomaly was causal or coincidental. Statistical significance requires multiple events. Until more interstellar comets are observed and analyzed, the hypothesis remains in a gray zone between plausible and unproven. This accumulation of uncertainties does not mean that nothing is known. The magnetometer flicker was real, a coherent, multi-station signal that passed standard tests for data quality. The timing coincidence with 3I/Atlas was real, within the limits of orbital calculations and propagation time estimates. The characteristics of the flicker, its amplitude, duration, spatial pattern, were consistent with known magnetospheric processes, even if the trigger was unusual. What the uncertainties mean is that multiple interpretations remain viable. The flicker could have been caused by the comet. It could have been caused by a small solar wind structure that happened to miss the spacecraft monitoring the solar wind upstream. It could have been caused by internal magnetospheric dynamics that occurred coincidentally during the comet's passage, without additional evidence. These alternatives cannot be definitively separated. This is frustrating but not surprising. Nature does not always present clear, unambiguous events. Most phenomena exist in a continuum of scales and intensities, and distinguishing signal from noise often requires large data sets, repeated observations, or fortuitous circumstances that allow detailed measurement. Science proceeds by narrowing uncertainties incrementally.